On Raoult's law, we talked about a two-component system in which component 2 was the more volatile of the two components, so its pure vapor pressure, the pure liquid vapor pressure, would be greater than the pure liquid vapor pressure for component 1. That's something I've captured up here. And then we found that you could express the total vapor pressure of their mixture as follows, as a function of the mole fraction of component 2 in the solution phase. Remember that we designated Y2 as the mole fraction in the vapor phase. Now I want to do a little bit more examination of this liquid phase versus vapor phase, but let me first just draw what we got at the using Raoult's law for the vapor pressure of our mixture containing both 1 and 2. All right, it was basically shown to be a straight line where at the low end it's the vapor pressure of the pure liquid 1, and at the high end it's the vapor pressure of the pure liquid 2. And the horizontal axis is basically just the mole fraction of 2 in the solution phase going from 0 to 1, and we're graphing here the total vapor pressure. So what we've graphed along this line is essentially the total vapor pressure as a function of the mole fraction of component 2 in the liquid phase. Now what I want to explore is there another way to view this, and will it give us more information? And in particular, I want to examine this vapor mole fraction and see what that can tell us about this solution. We'll remember that the mole fraction in the vapor is going to be given by Dalton's law of partial pressures as the partial pressure, the vapor pressure of component 2 divided by the total vapor pressure. So we can furthermore write that as simply the mole fraction of component 2 times its pure liquid vapor pressure, and then divide it by total vapor pressure, which is given up here as P1 star plus X2 P2 star minus P1 star. All right, so all I've done is use our Raoult's law to indicate this vapor pressure of component 2 and the total vapor pressure expression down here. Now what we can do is we can use this expression, because it's relating y2 and x2, we can use this to actually write x2 as a function of y2. So in other words, if I were to invert this relationship, I would find that x2 could be written as follows. It is equal to y2 times p1 star in the numerator divided by p2 star minus y2 times the difference in the two pure substance vapor pressures. Make sure this looks correct. Okay, so now we have an expression for x2 in terms of y2. What if we took this expression now and substituted it in for x2 in the expression for p total? When we do that, and I'm not going to go through the gory details of this, but we'll get an expression of the total pressure as a function now of the mole fraction in the gas phase. And in case you want to try this out at home, I'll show you what the answer is, but I'm not going to derive it for you. Okay, it's y2 p1 star p2 star minus p1 star divided by this same denominator over here, p2 star minus y2 times p2 star minus p1 star. All right, so this gives us now an equation that we could technically graph. Would we get the same graph that we've drawn over here, this straight line? Well, we can't, because y2 appears both in the numerator and the denominator here. All right, so we're not going to get a straight line. However, we can reassure ourselves that we're seeing the same limit. So for example, if I were to consider the limit as y2 goes to 0, all right, then the second half would totally disappear because I've got y2 multiplying this thing up in the top, and that means that the total pressure would then be approaching the pure vapor pressure of component 1. If I let y2 go to 1, and I hope you can convince yourself of this, but in that instance I would find that the total vapor pressure basically approaches P2 star. So it has the right limits. It's going to begin here and it's going to end here. All right, but when I draw this out as a graph, so I'm graphing this function here, as I draw that out, I will end up with a graph that looks something like this. All right, you'll notice that it's curved, and so it's not a straight line like the other one is. This is what it looks like when I graph the total vapor pressure as a function of the mole fraction of component 2 in the gas phase. Now, what can I get from this particular graph? Well, first of all, I can see readily that the graph, when I'm graphing it in terms of the vapor phase mole fraction, lies below and to the right of the solution phase. So for example, if I'm at a particular pressure, let's take a pressure like around here, and I come across here, this would be the mole fraction that that pressure would correspond to, the mole fraction in the solution phase. So if I come down here, this would give me the X2 for a solution that would give me this total pressure. But in the vapor phase, for this same total pressure, it would actually be a point over here. So we can see that it has mapped into a vapor phase that has a higher mole fraction. It's over to the right of the solution phase mole fraction. This line that connects these two dots is something called a tie line. All right, and these things are related to one another because if I were starting up here, and up here represents solution, so let me mark that. So up here I'm in solution, the liquid. At high pressures, I'm going to be in the more condensed phase. At low pressures, I'm going to be in the less condensed phase. So I'm solution up here and vapor down here. As I'm up here, if I am gradually lowering the pressure, so I'm gradually moving toward here, what I would find is when I reach this point here, that's when my solution would begin to vaporize. It would basically begin to boil. All right, but as it boils, the part of that solution that's more likely to enter the gas phase is the one that's more volatile. So the more volatile component goes into the gas phase. So what we find is that the gas phase will always be enriched in the more volatile component. And you can probably demonstrate this to yourself mathematically from all of this above. For example, from this expression and substituting x2 p2 star up here for the p2 in the numerator, we would find that y2 is equal to p2 star over p tote times x2. But p2 star up here is always greater than, or at best equal to, the total vapor pressure. So that means that y2 is always going to be greater than, or at best equal to, x2. So y2 is always going to lie over to the right of x2 because it is the more volatile component.